Okay, this is a video lecture for Math 110, and the topic today is arithmetic sequences. This video lecture is for Friday, April 10th. If you guys remember last class, we talked about sequences and series. And sequences, what a sequence is a pattern of numbers that's listed in a prescribed order. And a series is the sum of a sequence. Okay, an arithmetic sequence is a particular type of sequence in which each successive term of our sequence is obtained by adding a fixed amount d to the previous term. Let me repeat that. An arithmetic sequence is a particular type of sequence in which each successive term of the sequence is obtained by adding a fixed amount d to the previous term. Okay, what I want to do first is I want to write some sequences on the board, and you guys can tell me whether these sequences, or I will tell you since it's a video lecture, whether these sequences are arithmetic sequences. So one example I could write is 3, 5, 7, 9, 11, 13, and so on. Okay, here we have a sequence. Okay, is this an arithmetic sequence? The answer is yes, because each successive term, for instance 7, is obtained by adding a fixed amount to the previous term. 9 is obtained by adding that same fixed amount. And in fact, we can identify this fixed amount d as equal to 2 for this sequence. So each term of the sequence is obtained by adding 2 to the previous term. Okay, this is an arithmetic sequence. Let's consider this sequence here. Okay, is this an arithmetic sequence? This is not, because there's not a fixed amount we're adding to each term to get from the previous term to get the new term. For instance, with 4 here, we add 2 to 2 to get 4. But for 7, we add 3 to 4 to get 7. For 11, we add 4 to 7 to get 11. Now there is a pattern to this. We keep on adding one more to each term. But this is not an arithmetic sequence because the amount we add is not staying fixed. So this is not an arithmetic sequence. One other example I could consider is this. Is this an arithmetic sequence? Okay, is this an arithmetic sequence? This is not, okay, because again, there's no fixed amount that I'm adding to each term to get each term from the previous term. In fact, this sequence we encountered last class, and this can be represented by the expression an equals 1 over n. This is not an arithmetic sequence. This one is. So today we're going to focus on just arithmetic sequences. And what I'm going to do is I'm going to try to derive a formula for each term of an arithmetic sequence. So if you remember yesterday, certain sequences were given a formula for that sequence, and we could calculate every term of the sequence based on that formula. So let's see if we can find a formula for an arithmetic sequence. And I'm going to consider this particular example. I'm going to start identifying terms of this sequence. A1 is the first term. That's simple. A1 is equal to 3. Okay. A2 is equal to 5. But what I'm going to do is I'm going to rewrite 5 as something else that's equivalent to it. I'm going to rewrite 5 as 3 plus 2. Okay? We're all agreed 3 plus 2 is 5. And then I'm going to rewrite this as 3 plus 2 times 1. Okay? 3 plus 2 times 1. Now you might wonder if I'm doing drugs at this point. I'm not, but there's a reason why. There's a method to the madness here. There's a reason why I'm writing 5 as 3 plus 2 times 1. I'm going to go to the third term, A3. A3 equals 7, but once again I'm going to rewrite it in a different way. 7 is equal to 3 plus 4. Okay? And I'm going to rewrite 4 as 2 times 2. So A3 can also be written as 3 plus 2 times 2. Let's do A4. And hopefully you guys are starting to see a pattern emerge here. A4 is 9. I'm going to write 9 as 3 plus 6. Okay, we're all agreed in that. And this equals, I'm going to write 6 as 3 times 2. 2 times 3. Okay, and finally, let's do A5. A5 equals 11. I'm going to write 11 as 3 plus 8. I'm going to write 8 as 2 times 4. So let's focus in on these expressions here. Let's see if we can identify a pattern. Okay, all these expressions start with 3. Well, what is 3? 3 is just A1. So if I want to write an expression not just for a particular term of this sequence, but I want to write an expression for any term, the a to the n term, a general expression, I would write a to the n equals 3, right? Equals 3. Okay. Plus, now these also all have 2 here. These all have 2, so I'd write 3 plus 2. If I'm interested in calculating the a to the nth term, I write 3 plus 2 times. Now what's going on here? Let's focus in on this last bit. What's going on with these terms? Well, they're incrementing up. They're going from 1 to 2 to 3 to 4, and so on. Now notice this. We have A2 and we have a 1 here. We have A3 and we have a 2 here. We have A4 and we have a 3 here. We have A sub 5 and we have a 4. It seems like this number is 1 less than the index for each of these terms. And that is true. Well, the index is n. So, for instance, if this was A2, I would take 2 minus 1 to get 1. If this was A5, I would take 5 minus 1 to get 4. If this is AN, if it's AN, what I do is I take n minus 1. So this term is actually n minus 1. When n is 2, it's 1. When n is 3, it's 2. It's always n minus 1. So this is now a formula I can use to calculate any term of this sequence, of this arithmetic sequence. Now let's look at these numbers. What is 3 here? Okay, 3 is 3, but 3 is also A1. So we can identify 3 as being A1. All right. And what is 2 here? For this particular sequence, 2 is our D. So this is D. Okay? 3 is the first term. 2 is our common, they call it the common difference or common sum. So this is the amount we keep on adding to each term to get the new terms. So I'm going to make this formula. This formula is true for any term of this particular arithmetic sequence. But what I want to do now is write a formula that generalizes to any arithmetic sequence. So for any arithmetic sequence, the a to the n term can be written as a1 plus d times n minus 1. That's an important formula. I'm going to box this formula. Now, you don't have to memorize this formula. I'll give this to you guys for the test or whatever you might need it for. But this is a formula that gives us, so if we have an arithmetic sequence, and we know the first term of the arithmetic sequence, and we identify the common difference d, okay, we can calculate any term of that arithmetic sequence using this formula. All right, let us consider what the sum of an arithmetic sequence is. So I'm going to erase this. If you guys remember, a series is the sum of a sequence. In particular, what is the partial sum? And a partial sum is the sum of a sequence up to a certain amount of terms. So in this case, I'm going to ask, what is the partial sum of an arithmetic sequence? What is the partial sum of an arithmetic sequence? Okay. Now, there's a really beautiful proof. There's a beautiful derivation of the formula I'm going to give you guys. And it's not too hard. And I'd encourage you guys, if you're curious, to check out that derivation. It's in the book. But in the interest of time, given everything going on this semester, I'm not going to go through that derivation. I'm just going to give you guys the formula. Okay, the formula for the partial sum of an arithmetic sequence up to the term n is equal to n times a1 plus an over 2. Okay, I'm going to box this formula. This is an important formula. Again, this formula gives us the partial sum of an arithmetic sequence, only valid for arithmetic sequences. Again, the partial sum, s sub n, is equal to n, the index, so the last term you're summing up to, the index of the last term you're summing up to, n times the first term plus the last term of that you're adding up to in the partial sum divided by 2. Okay. Let us do a couple examples here where we apply these formulas to 3 different examples, and 2 of them are real-life examples, but the first example we'll consider is a bit more just purely mathematical. So the example I want to consider is, these are examples. Example 1 is the following sequence: 5, 9, 13, 17, 21, and so on. Okay, first of all, is this an arithmetic sequence? The answer is yes, because each term is obtained by adding a fixed amount to the previous term. Okay? And an important first step with the sequence is to identify what that fixed amount is, the common difference. Well, you guys can see pretty quickly the common difference here is 4. We're always adding 4 to the previous term to get the next term. Okay? Let's also identify A1. A1 is 5. Okay? Important to do those 2 things before we go further. And in this example, what we want to do is find, so the first part of this is let's find the 40th term, a sub 40. What is the value of a sub 40? Okay, so we know a1 is 5, a2 is 9, a3 is 13, and so on. What is the 40th term? Now, if you felt like working really hard, you could actually list out every term of this sequence, all 40, up to 40 terms to find a40. But there's a shortcut to this. And the shortcut is to use our formula we just derived. An equals a1 plus n minus 1 times d. Okay? We can use this formula to find a40. So in particular, a40 will be equal to the first term of this particular arithmetic sequence, which is 5, plus, now here, the index here is 40. I'm interested in the 40th term, so n is 40. So I plug in 40 for n minus 1 times d. In this case, d is 4. This is what I get. And I get 5 plus 39. 40 minus 1 is 39 times 4. And if you guys plug this in your calculator, you get 161. So the 40th term of this arithmetic sequence is in fact 161. Another question we were interested in is, what is the partial sum of the first 40 terms? So we want to find this partial sum of the first 40 terms. Now, if you want to work really hard, you could write out the first 40 terms and then add them all up in your calculator. There's a shortcut to this, and the shortcut is to use the formula I gave you guys. Let's write that formula generally just to remind you guys. The partial sum of an arithmetic sequence is equal to n times a1 plus an divided by 2. Okay, we're going to apply this formula to this particular arithmetic sequence. So s sub 40 is equal to, this means our index is 40. So n is 40. Okay, the first term of our sequence is 5. The 40th term of our sequence, the 40th term of the sequence, a sub 40, is 161. So we plug in 161 for a sub n, because a sub n corresponds to s sub n. When we have s sub 40, that means we have a sub 40 here. So we plug in the 40th term of our sequence, 161. We divide all of this by 2. And if you guys plug this in your calculator, you should get 3,320. So this is the partial sum of the first 40 terms of this arithmetic sequence. I need to go check on something on my computer. I'll be right back. Okay, what I'm going to do now is consider 2 more real-life applications of arithmetic sequences, and I hope you guys enjoy these. One of them has to do with a job, starting a job you might take after college. So these are more examples. And let's suppose you guys have a job which offers you a starting salary equal to $50,000. Okay, and this job gives you yearly pay raises. Yearly pay raises of $2,200. Okay? So you're offered a job, you have a starting salary, you get yearly pay raises of $2,200. And we want to ask ourselves some questions about this job. First question we want to ask is, what is your salary? What is your salary in the 10th year? In other words, after 10 years in the job, what is your salary? Okay, let's think about this. If you were to look at your salaries year by year, if you were to write out your salaries, right, we can start writing them out. First, your year one salary is $50,000. Your year two salary is you add $2,200 to that. This should be $50,000. You get $52,200, and so on. If you were to write out your yearly salaries, this would be, I hope you guys see this is actually an arithmetic sequence, because each year you're adding a fixed amount. Each year you're adding a fixed amount, $2,200, to your yearly salary. Excuse me, to your initial salary. You're adding a fixed amount. So this is in fact an arithmetic sequence. Okay, this is an arithmetic sequence. Okay, and that means we can use the formula a sub n equals a1 plus d times n minus 1. Okay, we can use that formula to calculate the salary for any given year. In particular, in this part, we're interested in your salary in year 10. Your salary in year 10 is a sub 10. It's the 10th term of this arithmetic sequence. So to calculate this, we plug in our year 1 salary, which is $50,000, plus D. Now let's identify D here. D is the common difference. D is how much we add each year, the previous year's salary, to get the new one. I hope you guys see D is 2,200. So we're going to add 2,200 D times n minus 1. In this case, n is 10 because we're talking about the 10th term. So we get 10 minus 1. And if you guys calculate this, if you plug this in, you get 50,000 plus 2,200 times 9. And if you guys plug this in your calculator, you get $69,000. Okay, so in the 10th year at this job, you'll be earning $69,000. Now another question we can ask about this job is how much money will you earn in the first 10 years? How much total money is earned in the first 10 years? How much money is earned in the first 10 years? Okay, so in this case, we're not so much interested in our salary in the 10th year, but if you were to add up the salary for the first year, add up the salary for the second year, add up the salary for the third year, and so on, you know, if you added all that money up after 10 years, how much money would you have? Well, what this is just a partial sum, right? This is just a partial sum of our arithmetic sequence for the first 10 years. So what this total amount is actually S sub 10. It's the sum of the first 10 years of your salary, the sum of the first 10 terms of this arithmetic sequence. Okay, we can use our formula for this, n times a1 plus an divided by 2. In this case, n is 10 because we're interested in the amount of money earned in 10 years. So n is 10. A1 is 50,000. A1 is our year 1 salary. A sub n is our 10th year salary, which we just found, which is 69,000. Plug that in. We divide all of this by 2. And if you guys go through the arithmetic on this, your answer should come out to 599,000. So if you added up your salaries for all the first 10 years, you get $599,000. Okay. Does this seem like a reasonable answer? Let's say you had no pay raises in this job. Let's say you started at $50,000 and every year you earned $50,000. How much money would you have earned after 10 years? The answer is you would have earned 10 times 50,000, which is 500,000. Okay. This is more than that. It's more than that because you're getting yearly pay raises. So this answer actually makes a lot of sense. This answer makes sense that if you're getting these yearly pay raises and you're adding up all that money, that you're going to get more than, you're going to earn a total that's more than 500,000 than just 10 times this. So this answer seems pretty reasonable to us. Okay, I want to do a third example problem with you guys, having to do with arithmetic sequences. This example has to do with auditorium seating. Okay, and the problem is this. We have an auditorium, and it has 60 total rows. So there's 60 rows in our auditorium, and the first row has 50 seats. And each successive row has 4 more than the previous. Each row has 4 more seats than the previous row. So we have an auditorium with 60 rows, okay? 50 seats in the first row. Each row is 4 more seats than the previous row. What would this auditorium look like? It would actually kind of look like a shell shape here. This would look like, so your first row has a certain number of seats, 50 seats actually, and each row you're adding 4 more seats, so the rows would get progressively longer. This is kind of like a Greek amphitheater, if you've ever seen one of those, or it's an amphitheater type seating structure. And the question is, we want to ask ourselves, the question here is how many total seats are in this auditorium? So, or in other words, what's the total seating capacity of this auditorium? Okay, so what's going on here? We've got various rows of seats. If I were to write out the rows, in the first row, I have 50 seats. Okay. In the second row, I add 4 more on, I get 54. In the third row, I add 4 onto that, I get 58. In the fourth row, I get 62, and so on. Okay, so I keep on adding on seats to these rows. What is this? This is an arithmetic sequence. This is an arithmetic sequence. And let's identify the first term as A1 is 50. It's the number of seats in the first row. And what is my common difference, D? Common difference, D, is 4. I keep on adding 4 seats onto the previous row. Okay, so, but in this problem, I'm interested in calculating the total seating of this auditorium. Okay, so I'm not really interested so much in how many seats are in each row, but if I add up all the seats, if I take 50 and then I add 54 and I add 58 and 62 and so on, you know, that's the total seating of my auditorium. What is that seating? So I'm really interested in a partial sum, right? And I'm interested in a partial sum of all these rows. Now the question is, which partial sum am I talking about? Well, this auditorium has 60 rows. So I want to sum up all 60 rows. So the partial sum I'm talking about is S sub 60. I'm adding up the first 60 rows to this auditorium. In other words, all the rows of it, but the first 60. So I'm interested in S sub 60. I can now use my formula in for a partial sum of an arithmetic sequence. Okay, over 2. Now, in this case, our index is 60, so I can plug in 60 for n, so I get 60 for n. A1, I know, is 50. I have 50 seats in the first row. Now an is a sub 60. An is the number of seats in the 60th row. This is a sub 60 divided by 2. Now the only problem here is I don't know what a sub 60 is. I have to know what a sub 60 is to plug it in here to calculate the partial sum. I don't know what a sub 60 is. But the good news is I can calculate it. I can calculate it by using our formula, a sub n equals a1 plus d times n minus 1. That's our formula for any term of an arithmetic sequence. In particular, I'm interested in a sub 60. A sub 60 will equal a1, which is 50, because a1 is the number of seats in the first row, plus my d. Here d is 4, right? D is 4, so I take 4 times n minus 1. In this case, n is 60, so I do 60 minus 1. This equals 50 plus 4 times 59. And if you guys calculate this, a sub 60 comes out to, let me find this on here. Where are you? A sub 60 comes out to 286. 286, okay. So there's 286 seats in the 60th row, okay. So now knowing that, let me just erase. I'm going to need to find a little more room here, so I'm just going to erase. I'll erase this here. We got this formula. I know. So now I know a sub 60 equals 286. I'm just going to erase what's below this. Okay, and now I can plug this into my formula for the partial sum. S sub 60 equals 60 times 50 plus a sub 60 is 286 divided by 2. Okay, I plug that in. And if you guys plug this in your calculator, you get 10,080. So the total seating capacity of this auditorium is 10,080 seats. Okay. This concludes the lecture on arithmetic sequences. Basically, to summarize, we talked about what an arithmetic sequence is. It's a certain type of sequence in which each successive term is obtained by adding a fixed amount d to the previous term. And then we did some examples of applications of arithmetic sequences to everyday life. I will see you guys on Friday.